Hello everybody, welcome to 2023 International Conference on Disaster Mitigation Technology for Smart Infrastructure. This presentation is focused on a research performed by Professor Chang and me on the backbone curve prediction of bridge piers through a stacked bidirectional LSTM network using a slow and fast cyclic test. This presentation is driving the trend toward addressing the prediction of the entire force time history of bridge piers using a slow and fast cyclic test. The scope and objectives of this presentation are briefly highlighted here as utilizing a deep learning technique to predict the entire force time histories of bridge pier using a slow and fast cyclic test considering axial load effect, implementing various input variables through cross-functional API, proposing a stacked long short-term memory LSTM network together with a bidirectional LSTM to predict the entire force time histories, employing NVIDIA GPU-based LSTM to accelerate the training runtime, utilizing the predicted force time histories for hysteresis and backbone curves prediction of unseen dataset or future specimens, reducing the experimental and computational costs for upcoming slow and fast cyclic tests, resulting in a robust performance for experimental unseen dataset and a fast and accurate insight into structural hysteresis behavior. A two-span bridge structure is selected in this study for fast and slow cyclic test. A scaled size RC pier was manufactured as an experimental substructure for the test according to Korea Road and Transportation Association. Cyclic tests help to leverage the potential of the servo-hydraulic actuator system to conduct experimental tests in order to investigate the seismic response of structures by applying a displacement history defined in the loading protocol to a test specimen. The most important pros of cyclic tests are the possibility of having the information associated with the yielding strength, ultimate strength, hysteresis behavior, energy dissipation capacity, strength deterioration, ductility, and collapse load. The experimental setups of various bridge piers for fast and slow cyclic tests are presented here, including different nominal and effective height, different cross-section, circular and rectangular. FLF was installed at the top of bridge piers to apply the axial force effect. This setup manufactured and conducted at his stake, Myongji University, 4 in 2017, 5 in 2018, and 8 new tests in 2022 to consider the effect of various input parameters on the force time history prediction. The characteristics of the test setups, including 10 fast and 7 slow cyclic tests, are listed in this table. It should be highlighted that a pier experiences the same displacement path and axial load during fast and slow cyclic tests, but with a 100 times slower velocity for a slow cyclic test. The test involves multiple input variables, including horizontal actuator displacement, vertical load, effective height, moment of inertia, and mass. The last column denotes data splitting for training, validation, and testing data set. It should be noted that low pass Butterworth filter with a cutoff frequency of 5 Hz is applied to the horizontal and vertical actuator forces to minimize the disturbance from the oil column resonance. LSTM is a significant improvement of recurrent neural networks RNN that makes the possibility of solving the struggles associated with line-term dependency. The main advantage of LSTM is remembering information for line periods by adding the cell state to RNN. It performs well for time series data such as nonlinear behavior prediction of displacement time history under seismic excitations. Despite remarkable results reported for the LSTM network, it may face an overfitting problem due to neglecting the information including upcoming features. So, bidirectional LSTM has been developed and widely accepted to overcome this shortcoming by training the input sequence in both the forward and backward directions, and finally concatenating both interpretations. A plot of the proposed stack by CUDA and LSTM model is graphed here. The proposed deep learning prediction model includes input layer, two bidirectional CUDA and LSTM layers, a concatenation layer, two bidirectional CUDA and LSTM layers again, and two time distributed dense layer, and finally an output layer. The time distributed dense layers apply the same layer to several inputs and produces one output per input to get the result in time. Therefore, it can be very beneficial to work with time series data. The input layer involves several features as horizontal actuator displacement, the right and left vertical actuator forces, and the effective height of bridge pier, the moment of inertia, and mass. It is required for the LSTM network to define the input variables in a 3D format as number of samples, the first values for fast and slow cyclic tests, for example, time steps, TS, the second values, and features or window size, the third values for fast and slow cyclic tests. Number of samples, for example, for fast cyclic tests are selected to be 6 including 4 training and 2 validation dataset, and in a repeated manner is selected to be 5, including 3 validation and 2 3 training and 2 validation datasets. Here we used a stacked scheme for the bidirectional code LSTM layer to obtain a faster and more accurate prediction of force time history for cyclic test. Due to a long sequence of time series data, window size or the size of each stack of 40 and for fast cyclic test and 20 for slow cyclic test are optimized through greater CV class for deep learning model with Python cross library, resulting in the best prediction. It is noteworthy that the initial length for the initial length of data for a slow cyclic test was more than 2 million. So windowing process helps to reduce the length of data and avoid training runtime difficulties and out of memory errors. It should be highlighted that the data for tests conducted in 2017, 2018 and 2022 are different in terms of length. So zero padding is applied for all the input variables to have the same size of variables during training, validation and testing processes. As a result, the number of stacks for each input variable becomes equal to 1197 and 2395 for fast and slow cyclic tests. As can be observed in this plot, a unit of 200 is selected for bidirectional code and LSTM layers for both the forward and backward direction, resulting in a unit of 400 totally. And concatenating the 6 input feature resulting a unit of 2400 totally, and the number of units for time distributed dense layers are optimized as 150, and finally the output layer result in one step in time history of force time history. A workflow diagram of the step-by-step process of the proposed approach is presented in this plot, including reshape the input and output features to a 3D array format. As mentioned in the previous slide, scale the data in the range of 0 and 1 using a scalar and preprocessing min-max scalar. As the LSTM algorithm and generally deep learning models are drastically sensitive to data scaling, unscaled input variables result in an unstable learning process with large errors. So scalar preprocessing min-max scalar of Python library is hired here to scale the data in the range of 0 and 1. It is worth mentioning that after prediction, all the training, validation and testing processes The scale data should be inversely transformed to the original values to be used for comparison purposes. Stack the data using optimal window size, as mentioned in the previous slide. It should be noted that n stands for the number of time steps in the original data set before stacking. Define the input and bidirectional CodeNN LSTM layers for each input variable using cross-functional API to consider multiple input features. Concatenate the above layers and define bidirectional CodeNN LSTM time distributed dense and dense or output layers. Compile the stacked bidirectional CodeNN LSTM model using Adam optimizer with the determined learning rate and decay, and set optimal batch size and best loss. Shuffle the training and validation dataset with a ratio split of 3% for validation, and then calculate the validation loss. If this criteria is satisfied, best loss will be equal to validation loss, and the loop will be ended. As can be observed in these figures, both the training and validation losses for fast and slow cyclic tests are monotonically decreased and reach 0 after 5,000 epochs. It should be noted that mean absolute error is selected here as a loss measure. A comparison of the predicted and experimentally measured force time histories for validation and for validation data set confirm that there is a good compatibility between observation and prediction values, especially for the maximum values. 3 different measures are investigated to visualize the prediction error in order to get a sense of how reliable the predictions are, as presented the correlation coefficient, box Whisker plot, and the histogram including the Gaussian distribution of the prediction error, the risk curve. By using the last 2 measures, it is possible to see more clearly how the prediction errors are distributed across all the data set in a time series. As can be observed in these figures, the correlation coefficient is higher than 96% for both piers number 5 and 6, and also the mean value of normalized prediction error is close to 0. In addition, it can be inferred from the histograms that the majority of the normalized prediction error falls between -5 and 5%, as can be observed in these figures. Therefore, the validity of the proposed by CodeNN LSTM model is further supported. The predicted force time histories in the previous step are then used to map the hysteresis and backbone curves for the piers number 5 and 6. As can be observed in these figures, there's a notably agreement between the observation and prediction values. To further justify of the prediction deep learning model, in this slide we go through unseen dataset or future dataset. As can be observed, the prediction model works well for unseen data, and there is a good compatibility between the observation and prediction time series data. The same explanations for error meters are approximately valid here for unseen dataset. And finally, the hysteresis and backbone curves of the unseen dataset for fast cyclic tests are derived from the predicted force time histories from the previous step, and there is a good compatibility between the prediction and observation dataset. There's a plan here to compare the observation and prediction for some histories of validation dataset for a slow cyclic test, as can be observed from the result. It can be observed, it can be inferred that the prediction deep learning model is satisfied with highly correlated prediction dataset. From the error meters, it can be determined that there is a higher correlation coefficient, more than 99%, and lower normalized prediction error, mostly close to 0 for a slow cyclic test. The previous result can be confirmed here with the graphed hysteresis and backbone curve. Subsequently, further validation for a slow cyclic test can be obtained using a testing dataset. To get much more insight into the behavior of fast and slow cyclic tests, a performance comparison of the predicted and experimental hysteresis and backbone curves of the testing dataset is presented in this figure. As can be observed from the figures, the slow cyclic test has the priority in prediction results for the test dataset compared to the fast slow cyclic test. Finally, with having all the results, it seems that we can trust by good NNN LSTM prediction model in different engineering fields for its accuracy, speed, reliability, and comprehensibility. It helps to save time and cost to manufacture and conduct new experimental tests and have a fast and accurate intuition of a structural hysteresis behavior. Thank you so much for your attention. The authors gratefully acknowledge the financial support provided by the Brain Pool program funded by the Ministry of Science and ICT through the National Research Foundation of Korea and Hybrid Structural Testing Center at Myongji University.